Hi, my name is Shannon Cappallezzi. I am a project scientist for the Soil Health Institute based out of North Carolina. My station area is at Oregon State, and right now we are at the University of California Westside Research Extension. So we are working on what's called the North American Project to evaluate soil health measurements. It is a North American project. We have sites in Canada, in the US, and in Mexico. There's about 125 different sites. On those 125 sites distributed throughout North America, we have 2,000 experimental units. Each plot is considered an experimental unit. So all of the sites that we have chosen are at long-term research sites. So all of them have had the same type of management for at least 10 years. And this allows us to have a lot of strength in what we're doing. We're doing a one-time shotgun sampling where we go out to these 2,000 plots and sample everything all in 1 year. But because they've had the same management for a long period of time, we expect that they're in some kind of almost steady state as far as this is what we would expect from this management unit. And because we have replicated treatments, we expect that we'll actually be able to understand the variation between treatments and between plots and have a better idea of how different types of management impact the soil health and whether or not the measurements that we're using in order to evaluate soil health are sensitive enough to pick up differences in management and are appropriate for what we are trying to learn and describe, not only about the soil chemistry, which is what we have typically looked at in soil testing, but also in the physical properties that are largely driven by the biological community. So within this project, we are doing a large number of different biological tests, including a full genome sequencing. We're using PLFAs, phospholipid fatty acids, to understand microbial groups. We're doing a suite of enzymes to understand more of what the microbes are producing in order to break down and cycle those nutrients. We're studying the microbial respiration. The CO2 that comes out of a soil is a result of microbial metabolism. That activity is very important for the soil, for building structure, for cycling nutrient, for doing all of the functions that we want to see in a soil, the things that we are asking the soil to do for us. So whether it is storing water, infiltrating water, cycling nutrients, building structure, and the habitat for organisms, all of these things are driven largely by one thing, and that is soil carbon. Soil carbon is really one of the largest indicators for whether or not a soil is healthy, and that's because most of the microbes that are in the soil are heterotrophic. They need carbon for their food and for their energy. If they don't have that carbon, they can't perform all of these functions that we want for a healthy, functioning soil. And so we have a suite of 39 different indicators. I talked about just a couple of them. A suite of 39 different indicators that we are measuring that include biological, chemical, and physical tests from a number of different soil labs throughout the country. And we are very excited to see how well our North American assessment of soil health metrics works out. So one of the measurements that we are performing at each one of our experimental units is bulk density. Bulk density is a measure of the mass of soil in a given unit of volume. And so we have two different ways that we're doing this. We are doing what we call bulk density, where we're using just a metal ring. We are driving this into the soil surface and putting it into a bag, 2 of these in each of the plots. We're also taking 2 intact samples in each of these plots. These intact samples will be used for a measure of bulk density so that in each plot we have 4 basically representative areas for bulk density. But we're also going to be trying to do some intact measurements in the laboratory. One of them is available water holding capacity. Available water holding capacity is the amount of water that a soil holds between field capacity and wilting point. That's the water that is available to plants. Most of the time when this is performed in a lab, the soil is dried and ground and then put into a small metal ring. We're using intact samples because the soil structure has a huge impact on how much water the soil can hold. And so we are hoping that by taking these intact rings, we will be able to get a measurement of both bulk density and available water holding capacity in an intact way. So first I'm going to show you what we do with the metal ring. It's a little bit easier. I come down here, I just kind of clear a little bit of the organic matter away. We want to start right at the mineral surface. We take a metal ring, level area, some kind of wooden block. This one's gotten beat up a little bit through some of my sites, but any kind of little wooden block will work. Put this right on the surface, take my mallet, and this wooden block helps to distribute the weight so that it goes straight down so that we're not creating channels. And we're just going straight to the soil surface. I take my soil knife, hori, and I'm going to excavate out around the area. So if you can see the surface here, you can see that there's kind of some loose, crumbly, nice granular soil right here at the top. And I'm going to just kind of scoot it away a little bit so that I can get a nice level surface. I'll use the edge of my soil knife here. It has a nice flat blade. I'm going to take one of these lids and put it on top so that I don't lose what I have right on the top of it while I excavate. So I put that on the top, take my soil knife, and I dig down here enough so that I can get my knife underneath this ring. And I want to get this underneath so that I don't lose the material from the bottom. And then I'm going to bring it up and flip it over. And right now you can see that I have more volume than is in the ring. So again, I'm going to take this knife edge and I'm going to, almost as if I were making a cake and measuring my flour, I'm going to make sure that this is nice and even across the top. And now I've got a nice flat surface. I'm going to remove the material from the edges. This is going to go into my pre-labeled sample bag. I can dump that, take my lid off, remove the loose material from the top, and then push that soil out. Again, we're doing 2 of these from the metal rings for each plot, so that'll be an average of the 2 metal rings for this measurement. And then we're also going to do an intact sample. For purposes of this video, I'm going to do it right here, but normally we would spread this out throughout the plot. And again, I'm going to find a nice area that's relatively flat and representative of the plot. Now, taking it with these plastic rings is a little bit trickier because they can bend, they can break. So I'm going to hit it a little bit more gently. The other thing I'm going to do, as I'm hitting this plastic ring down, I'm going to rotate my piece of wood. Otherwise this warps and kind of squeezes in on the bottom, and we want to keep it as circular as possible. All right, we are at the soil surface now. And again, I'm going to take my knife, excavate around. Where it's loose enough, I can use my fingers. I've got a nice level surface. I have 2 different kinds of caps here. I've labeled some of them with top so that once they get to the laboratory, they know which side was up. Right on the top there, and then excavate down again. I've got a little bit extra on the top, which is actually just what we want to see there. That way we can slice a little bit off. And the lid there on the bottom, make sure that's tight, and we have an intact bulk density sample that we will also be able to run available water holding capacity using pressure plates at the lab. Well, one thing that I think was a really smart decision on behalf of the Soil Health Institute was that one of the 7 project scientists who is on this North American assessment, his main job is in large data management and building a database. So we have somebody who is specialized in dealing with large data sets, who is helping us to make sure all of our samples are properly put, everything is put into the right place in the computer. And he is also an expert in statistics. So he is going to be working with us to manage this really large data set. And then each of us have been given specific team leads. So part of my background is in livestock production. So all of the sites that have any kind of livestock incorporated into them, I will be helping to specially assess those for the impact of livestock. We have other people who their specialty is in genomics. And so when it comes to the genomics data and the relationships between the genomics data and the other indicators we're looking at, that will be her job. And so we have a diverse set of scientists who are working on this project, each of us with our own specialty, so we'll each take on a different aspect of the project, but we'll also all be working together to look at the data. Right now, we expect that we will have all of our sampling done by the end of June. Some of our sites in Canada are considerably later than, say, our sites in Arizona and Mexico. So we'll have all of our samples in by June. The lab should have all of the data back to us by the end of November. And so at the end of November, that will be our big push to work on analyzing the data. And then by the end of November the next year, we expect to have a lot of publications ready to go to the presses. We have many different ideas about how to analyze the data. Some of that will have to be driven by the data and by what we see. One of the first things we'll be able to analyze is the measurements from the Saturo, the saturated hydraulic conductivity, because we have that data now. So that will be one of the first things that we can look at. Other things like bulk density will also probably come back from the lab earlier than other analyses, because all it takes in the lab is weighing those, drying them and weighing them. And so we might be able to look at something like the relationship between the saturated hydraulic conductivity, the bulk density, the texture, and the management systems that we have in place.
Necessarily, but Shannon, we really are grateful and appreciative of you being here and doing all this work and the work that's yet to come and the work of the Soil Health Institute. So on behalf of our entire team down here, which has many, many different partners, we're thankful and we're very grateful to you. Have a good wrap up here and a good trip back to Oregon too.
Yeah, and this project would not be possible without the tremendous help from all of our site cooperators. It takes a lot of work to be able to put a project like this together, and the cooperation and the willingness to supply extra labor out in the field and resources as far as providing management history and an understanding of the site and help coordinating with logistics, that has been absolutely pivotal to our project and will be pivotal in the success. We do want to be able to work with our cooperators who have more expertise than we do, particularly about their sites in specific, but also broader. There are experts on each of these different indicators, and partnering with them will be one of the things that helps make our project really, really strong.